All right, so let's just dive in. So like I said, with any of this material, you can just go to jigsawlabs.io/free and then click on the curriculum and see it, read along. But for me, I'll just move to the note form. Okay, so this is our picture of a neural network. And what you can see is, these different circular things with the tentacles coming out. Each one of these is a separate neuron. And when the neuron's lighting up, we can imagine that that's the neuron firing. And here we can see this neuron maybe is not lighting up, and there the neuron is not firing. So what makes a neural network powerful and able to perform tasks like detecting whether or not this is the number 9 or another digit is really almost like a separation of concerns, where what occurs is neurons that are earlier in the network are looking at more concrete tasks. Like maybe they're looking, like neurons here are looking to see, are there straight lines in the picture? Is there a circle in the picture? Is there, a diagonal line or horizontal lines in the picture? And later on, neurons are then piecing together that information that comes through this firing or not firing of earlier neurons and taking that information and putting it together to say, oh, cool, there is diagonal line followed by another diagonal line. And that's telling me that this is, a circle here. And then maybe later neurons are saying, okay, these earlier neurons said there was a circle, and an earlier neuron said there was a vertical line. And I'm putting that together to say that I think this is the number 9. So the idea with a neural network is that we have almost like these layers where information is passed forward, and the earlier layers are making more concrete determinations, like determining whether something's a straight line or a horizontal line. And then later layers are maybe putting that information together to say, oh, here's a circle followed by a vertical line. And then maybe our last layer is putting that information together to say, cool, here's the number 9. So that's kind of the easiest way and shortest way I can explain neural networks. But it's obviously a lot more complicated than that. And really what we should do is dive into a single neuron. So a single neuron is itself taking in a lot of different information. And we'll see that a single neuron can be really, really powerful. So just to get a couple of terms out of the way a neuron takes in information is through the dendrites. So maybe this neuron is taking in all this information about this area right here, or maybe even about the entire picture. Just to say, are there even any light pixels on the screen? Maybe it's gathering information about these regions to make an assessment about that. Now, the dendrites are taking in information. What's actually then using that information and making the determination is the cell body. So that will say, okay, this thing's all black, or no, there's some light here, it looks like a valid image. And once it makes its determination, it then wants to communicate that information to other neurons. So it does that through the axon. And so when we say that a neuron fires, right, it's sending basically an electrochemical signal. Just think electricity, it's lighting up through the axon. That's what's triggering this chain reaction. And now that we've seen a neuron, this is a real image of a neuron, we should also just get familiar with a diagram of a neuron. So this is just communicating the exact same information. This neuron is taking in information, right? Taking in data, making a determination through the cell body, and then firing through the axon. And in the early stages, at least, we'll indicate that firing with a 1 and indicate a neuron not firing with a 0. So even though we're focusing in on a single neuron, single neurons can be very powerful. So for example, this is a pretty famous data set in data science called the breast cancer data set. It's from pretty early on. And what happened was a professor had, I forget if it was graduate students or nurses, basically record attributes of different cells. Right? How large is the cell, how many bumps is in each cell. And the point was to then take those attributes, and by looking at the size and the number of concavities among other attributes, use a machine learning algorithm to predict whether or not the cell was cancerous or not. And we can use a single neuron to do that, right? So you can see, like, here I'm kind of representing that data. And just to break this down a little bit, each row here, right, we only have two, you can think of as a separate example, a separate cell that's potentially cancerous. So this is maybe the first cell that we're looking at, and we see that the size is 0.4, and we also see that the number of concavities is 2. And then here's a second cell, right? Different area, different size, 0.6, and then different number of concavities. So right, this is just representing maybe 2 different cells, 1 and 2. And now let's just like add some terms, and these are general machine learning terms. So we'll say like each example or each row of data is an observation. So above we have 2 observations representing 2 different cells. And then we can break down an observation into the features, right? So there's features, which is each attribute of the observation. And I like to think of this, it's like you can think of features as an attribute of an observation, or even almost like input, right? Because if you think about it, these features are going to be used to predict whether or not a cell is cancerous. So these are kind of the inputs that are going to allow us to then predict, hopefully, whether or not a cell is cancerous. And what we're trying to predict, that is our target. So here, like, is cancerous, right? That's our target in this example, okay? And again, like this applies to machine learning in general. You know, you'll have these different observations, and we'll say like each example is a separate observation, and an observation consists of these different attributes or inputs that are then going to hopefully allow us to predict an output, you know, something that we're the goal. And here, is it cancerous? And the name for that goal, what we're trying to predict, that is the target. So just to remind us how this applies to our cell, right? We can imagine that we feed in information about, a potentially cancerous cell's area, potentially cancerous cell's number of concavities, right? These are going to, I guess, a separate dendrite in the model of our neuron. And then this information goes into the cell body, the neuron cell body. And from here, we get a prediction. Is it cancerous? Which to us is just a 1 or a 0, right? So we'll maybe pass in the number 0.4 and the number 2, 0.4 and 2. That will somehow go into some formula. And then based on that formula, we can predict, hopefully, whether or not the cell is, that breast cancer cell is cancerous or not. So let's see what this means in code. All right, so here's our data. Right, ultimately, we want to represent this using Python. Right, so let's start with just like a single observation. And so to do that, if you think about it, we could probably just assign a variable, one called cell area, and set that to 0.4. We could also do like cell concavities and set that to 2. Right? And then let's also pretend that we know that this cell is cancerous. So we'll say is cancerous, or cell cancerous equals 1. All right, so we'll say at this size, we'll change it to a 0. At this size and 2 concavities, we'll say that is 0. All right, and another word for this is just the target. So maybe we'll just call that target. And just to, introduce you to this a little bit early, in the future you'll see we can actually combine these features into a list, so we could say like, okay, here's our features of the observation, and that's maybe 0.4 and 2, and then the target is 0. All right, cool. Now, that's just the data. Remember, the point is to maybe pass through this data into a neuron and get back a prediction. So let's deal with that, and we'll stick with this format for now. All right, cool. And maybe we'll even, we'll keep that for now. So we'll write a function. We'll call this isCancerous. And if we think about what we want it to return, ultimately it should probably return a 1 or a 0. For now, we'll do something a little different. I'll show you in a second. So we'll do isCancerous, and these are the inputs, right? Cell area, cell concavities. And so this probably makes sense as function arguments. So cell area, cell concavities. And for now, we can just add them. And we'll just return the output. So we'll say isCancerous. Cell area is 0.4. Cell concavities is 2. Yay, we did that. So for now, what we can say, remember this ideally is going to return a 1 or a 0, right? Where 1 means isCancerous and a 0 means not. But for now, what we'll do is let's just say if it outputs a positive number, that is cancerous. If it outputs a negative number, then it's not cancerous, okay? And one thing you'll notice is that, like, for all practical purposes, it seems like our function will always output a positive number because cell area is always going to be at least something, right? It's always going to be like 0.1 or higher. And cell concavities, well, the lowest that's going to be is 0. So we're always going to output a positive number. So instead, in our formula, we need to update it. And normally you add something called a bias. So bias is just a counterweight to the rest of the function. So if here's like one part of the function, we're like adding up the features, then our counterweight would be like a negative number. Like let's just say like -4 for now. So now notice what happens, right? Now our function, we pass through 0.4 and 2. Here we actually get a negative number, which means that translates to a 0, okay? 1 is cancerous, 0 is not. Here we get a negative 1.6. So that looks like we get a prediction of not cancerous. Let's just try another one real fast. So do isCancerous. Let's say the size is like 0.6 and there's like 5 concavities, very bumpy, I suppose. And here we get a positive number, and that means that we're going to predict that it is cancerous. Cool. All right. So these are just predictions, right? Like that our neurons making. We'd have to assess later on, like actually, have a graduate student or a nurse, find the real answer and then see how good a job our neurons do. But this is the prediction based on these inputs. And so far, I suppose it's pretty good. I don't know if it's good at all, but maybe it's fine. So let's move on to doing this in math. If we saw how to represent this in code. If we want to represent this mathematically, we can. Oftentimes, this function is called like z of x. Okay, and we'll say z of x here. We'll just name this first feature cell area, and we could just say cell area, I suppose. And then plus cell concavities, right? Minus some sort of bias term. Let's just put in here plus bias, where our bias is -4. But really, more generically, oftentimes you'll see this represented as z of x equals x sub 1 plus x sub 2, right? Plus the bias term. So x sub 1 represents the first feature of a single observation, meaning here it's that cell area. And x sub 2 is that second feature, cell concavities, plus bias. So this really does translate to what we saw before of 0.4 plus 2 minus 4, right? And then we get some sort of output of like -1.6. And then as we pass through these other things, well, that means we have a different x1, a different x2, and therefore we get, a different output. Let's just see that. So that would be this 0.6 plus 5 minus 4. Right? So there's that number. All right, so this is how, the point is like, now you see how to represent this in math, right? It's just this z of x, x sub 1 plus x sub 2 plus bias, where bias in this case is a negative number. Now, one thing to, I guess, point out is if we look at our original function here, you can see, all right, well, we have this is cancerous, and we have these values of 0.4 and 2. And then we pass these through here. So this will give me that negative 1.6, okay, because just passing these through the chute. If I increase this cell area by 1, say to 1.4, right, well, the output just went from negative 1.6 to negative 0.6, so the output increases by 1. If I increase this guy by 1, from 2 to 3, again, the output increases by 1. Right, let's just do it again. See that? It's a little easier. So the point is, a change in cell area is having the same influence as an increase in the cell concavities. We're saying essentially that each feature here, cell area, cell concavities, they're both going to influence the prediction of our neuron equally. But that might not be what we want. Maybe we think cell area should be twice as important as cell concavities, and that if there's an increase in cell area from, say, 1.4 to 2.4, well, that output, the output here, should double, right? So let's just see that. The way that we can do that is just by adding a 2, right? This time we'll just multiply cell area by 2. So I pass through a 1.4 here, or let's even increase it to 2.4. The output here will not increase by 1, but will increase by 2, right? All right, so we did 2.4, we got 4.8 plus 4 minus 4, so these cancel out, so that gives us the 2 times 2.4 is 4.8. All right, but the point is, if I increase this by 1, what was this before? This was 4. If I increase this by 1, meaning 4 to 5, the influence is only 1. Right? The influence on cell concavities on our neuron is just 1, whereas the influence on cell area from 2.4 to 3.4 is 2. So what we're effectively saying is by adding weights, right, we are simply weighing features, having, of different importance, and having our features have different influences. Vary the influence on the output of the neuron. Okay, so this is kind of a cool thing, because we might imagine that, if you go back to this, well, there might be various features, and we might want to have our prediction function be more sensitive to a change in some features than other features, right? So we might say that, okay, maybe the color is very important, and therefore that weight might be even higher if we added in a feature for the color. Maybe that'd be like a 3 or a 4. All right, so this is kind of cool. It allows us to tweak the hypothesis function of our neuron. So again, we just saw this in code, right? Here's what it means to add our weights in code. And let's just see it now in math. So if this was our function before, now it's going to be, and x1 really represented cell area, or x2 represented cell concavities, and this was our bias, right? It was this negative 4. Well, now we would put this as z of x equals w sub 1, x sub 1, I'll explain this in a second, plus w sub 2, x sub 2, plus bias. Let's just put in the multiplication. All right. Let's take out the multiplication. So what's the point of this? The point is just okay, this is how we're representing what we call a function or a linear function with weights. Most people just call this a linear function, but I'll say linear function with weights. And you can see that there is a different weight for each of our features. So this was our cell area weight, W1. This was our cell concavities weight, W2. Here it's just the number 1. So just to translate this back, we would say, and then we'll kind of wrap up, we'll say that this is z of x equals 2 times by cell area plus 1 times biased cell concavities. All right, and that's looking not as good as I hoped. All right, better. Cool, so this is our function. And remember, plus the bias, minus 4. So, right, this kind of works. We can pass through some numbers here. It's going to give differing importance to cell area than cell concavities. Or another way of putting this is it will be more sensitive to a change in cell area than cell concavities. And we said that if this outputs a positive number, right, then we will make a prediction that it's cancerous. And if it outputs a negative number, then we will make a prediction that it's benign, that it's not cancerous. So let's just see that again. Take this here. And here it's a negative number. And because of that, we are not predicting cancerous. We increase this by a bit. Say this was a different cell. This cell, it's larger. And I guess that's the signal of, or increase the likelihood that it's cancerous. And so we are making a prediction that it's cancerous. All right, so that's it for now. The next lesson that we will go through is really, I guess, adding a bit of math or summarizing this function with a component of math. Then one more topic, and then actually we'll go right into building our first neural network. So I'll see you guys in the next lesson.